and then like I'll assume method which will return a boolean and path sum which will have the root and given sum. So one option is like if we need to track the current sum along the path, so I'll have another utility method. If root is equal to null, we can check if the current sum is equal to the target sum and then just return that. Because that path would have been exhausted. Else like we'll have sum on both left and right paths. So path sum on the root dot left, and this is the sum, and this is current sum will be, I can add the root sum also in this. Sorry, this should be Boolean. And similarly, I can do the right. And then return if one of them is true. I'm just thinking if this will work.
So your one base case is if the root node is null.
Mm-hmm.
And then what about the case? So we want to like check when we reach a leaf node, right?
Yes. So
like in the case of a leaf node, what do we want to check?
I'm just thinking if it's a leaf node, it's left and right will still have it will be nulls. So yeah, it'll unnecessarily go have another two calls, which we can avoid. I think.
Yeah, maybe before the left. Yeah. It's and some
Another
basic
condition.
Yes, yeah, to terminate the recursion.
Okay. So So here we can say sum is equal to current sum plus root dot well. Is this fine now?
Yeah, so like it's pretty close. I think
Yeah.
in my one, so in the first case, if root equals null, I just return false.
Okay, got it. Yeah, in this case, yeah, we can do that. So this is a leaf node condition, and this is the only place where we check.
Yeah. Return left or right. Yep, that looks good to me.
There's another approach if you want at the end.
Yeah, sure.
Okay, yeah, if anyone wants to take the control, yes, you can.
Right, and then we just call the helper with root, the same target sum, and current sum equal to 0.
So if the solution is okay, like I would let someone else take care and present some other approach. I'll stop the sharing.
Okay, sure.
Okay. Here, I hope you see it right now. Can you see my screen?
Yes.
Yeah. So first, whenever the case where it's the root is null, return false. If the so here we check if it's leaf, and if it's leaf, then we check if the sum minus the current value is null, then we return true. Otherwise, otherwise it just keeps going until it hits null and then returns false. So in this case, we go left and right, and if either of those returns true, then it's gonna return true. In short.
Okay. It's a shorter, avoids a helper function. Plus, you are just using the current sum instead of a new variable.
Yeah. So yeah, subtracting until it gets 0. Yeah.
Yep.
Okay.
Yep. Good. So does anyone have any questions so far before we move on to the next, like a follow-up question?
What's the time complexity?
Yes, great question. So does anyone want to answer that, the time complexity?
It's
Well, it should be a log of n, I would say. It goes left and right.
Well, in the worst case, we're gonna end up traversing the whole tree, right? Like, let's say if the sum doesn't exist.
Oh yeah, hold on, left.
it's 2 to the power of height of the tree. Oh,
Yeah, I think two.
oh yeah, that will be the full total number of elements, right?
Right.
Full
Yes.
order of.
So you're saying it's all n?
Yes.
Okay. Oh yeah, that's true. That's true.
Yep. Does everyone see why it's open? So in the worst case, we're not able to like eliminate either the left or right branch. We have to check both in every case. So we would be traversing the whole tree in the worst case. So it would be O of n. Okay, so now as a follow-up, and this is actually path sum 2 on lead code. What if instead of just returning true or false, if you had to return the actual a list of all the paths that sum up to the target sum? Anyone have any thoughts on how we might approach that?
So is it like all the paths, not just one?
Yes, all the paths that sum up to sum.
Maybe it's gonna be like with backtracking. or and then have a list of list.
Yeah, we'll have,
Maybe we can
yeah, sorry, go ahead.
do the backtracking using the list. So whenever if some condition is true, we can just print that list and remove the last element, so that whenever it is false, we can remove the last element. So for this function, I will just keep one more collection as a list, and I will keep the adding in the element in the list. And whenever the is-sum returning the false, I will just remove that element. And whenever the is-sum returning the true, that means that particular path is a valid path for the sum. I will print those all the present element from the list.
Okay. Like suppose that instead of printing, we want to actually return the list of the lists.
Yeah, we can do that. Instead of printing, we can return the list of lists. Yeah.
Would you like to share your screen and show us how you do that?
Yeah, I can do that.
Okay.
Just a minute. Are you able to see my screen?
Yep.
So
And just remember that there could be multiple paths, so the return
List of lists, right? Yeah.
list of lists. Yeah.
So what I'm doing here is that in the final list collection, I'm assuming that presently I'm working on the last list. Okay. And I need to add the current element in the last list. Maybe I will remove the compilation error later. If it is true, then I will start a new list so that we can. Okay, just let me get this condition first. If it is false, So in this program, what I'm doing, I'm just maintaining the final list first. And initially this list will be the empty list. And maybe I need to, in the start, I need to add one element in the list. And whenever we are checking the left node for the sum, I will add that left node to in the final list for the last element. And if the sum is true, that means we need to continue adding the element. It will work in the recursion, and whenever the sum is true, that means we got the complete list. And at that time, I will start the new list to find out the new path just by removing the last number.
Okay.
Or
Whenever the sum is 0, like the time this list is the final, right? So are you adding a new empty list somewhere, or?
yes, whenever the sum is 0, I need to add the new empty list in this final section.
Okay.
And maybe I will remove this compilation error, but logic will be more or less similar.
Okay, so have you tried testing this code, like lead code or something?
We can do that.
I think the node definition is different for him.
Yeah,
He's using some 3 methods, which is different from lead code. So
right.
he may need to do some modifications. I think in the call only you're trying to add. So I don't know if it still returns the same final call object.
Sorry?
In the isSum call only, you're trying to add this new left node, right?
Yeah.
So it essentially passes whatever the add method returns to the isSum.
Yeah, so instead of like adding every time and then removing, why don't we only add like to the final output if that path is equal to the sum?
So here you are saying, right? So we can, we can add only if its valid element. So in that case, I need to use the different method signature again. So just give me a minute.
Or maybe you can just do it before that line and then pass the final collection as is, right?
I can just pass the final collection as it is, and
Before that line, maybe you can add left node.
okay.
Do you need another
Now-
parenthesis to get it off? Okay, yeah.
Yeah, now it is fine, I think. Oh, okay. This is not correct. Okay. That's fine. Now inside the if, I will add in the, if it is correct, then only I will add in the final. So final dot get, it will, I need to find out the last element from the collection. So that is the
No, I
current
think
one.
you need to do before, because if it returns true, it would have already hit sum is equal to 0 and added a new empty list, right? So
Yeah, I can, yeah.
Hmm.
I can do the before, and in the else I can remove that.
yeah, so just to
So this will give me the last list, and then I will add the current node to that. Signature here.
I think you need to add the dot val.
Got
Yeah,
yeah.
dot get val. Yeah.
Yeah, that was the method signature. Yeah. And once if it is true, I will keep as it is. In the else, I need to remove that final dot. So here, it will just remove that data element. And similar to that, I will do for the right child as well.
Okay.
Right now. And maybe I can finally return the collection only. Just
No. Since it's a reference type,
Yeah.
wherever this is called, we can just return that.
I will keep that.
And then, so in line 24, right now you're just adding an empty array list, right?
Sorry.
So in line 24 is like, why are you just adding an empty array list?
I am adding the empty array list because suppose there are multiple array lists. So till this point, it is completed. Means I just got one valid list. Now I need to search for the next one, right? Okay, I cannot add empty, but I need to copy the previous one and just need to remove the last element, I think so. No, empty array list won't work. Yeah, I agree on that. So
Yeah.
I just need to remove the last element and need to again check for the right child, right? So
Yeah, I think you're on the right track. I mean, I could share my solution.
Okay.
yeah, you can share that.
Are you able to see my screen?
Yes.
Oh, okay, sorry. Yeah, so if I go back real quick to path sum 1, so this is pretty close to the solution that Martino and Naga had. So if let's suppose we have a separate helper function, right? So this is back to path sum 1. So we have this like current sum or sum so far variable that we're using to keep track of the sum as we go down the tree. So path sum 2 will be pretty similar. Instead of like, in addition to tracking this, we also want to store the nodes that we process as we move down the tree. So we'll have a list of integers called current path. And at every point we add that the current root.val to the current path. And then we have the same check here to see if we're at a leaf node and the root, the value equals the target, then we'll add this current path to our final output, which is our list of integers. And then we'll just return. Otherwise, if we're not in a base case, we will go both left and right. We'll subtract the current root.val from target, and we'll pass the same output reference, and then we'll pass a new array list containing the current path, which now has this this new node's value.
What was your runtime and memory usage? I'm curious.
Yeah, we could see that.
Yeah, I got the same 29.77.
Yeah, so there's probably more efficient ways. I'm not sure if that's, so as far as runtime complexity, I think this will also be O of n for the same reason as path sum 1.
Yeah.
Memory is more, I think.
Yes,
Memory
Memory is more
can-
because we're creating new array, no?
Yeah, so
Every
it can
time.
it can be easily tweaked. Basically, when we are at the line number 17, we are adding, right? And then 24 and 25, we are basically making duplicate.
Yes.
Mhm.
Instead of that, we can just pass the same thing. But when we return from that, we basically remove it.
Ah, yeah. I see.
So,
Oh,
so
remove what? The
current. So
current
line
one,
number
okay.
17. So at line number 26, before returning, we remove it. So we don't have to basically recreate it.
Mm-hmm.
And there is a single list that goes in. When we hit our condition, we make a copy to the output. Otherwise, we just keep doing it.
Okay, that's so maybe we could try that real quick. So we pass the same current path. And then after this returns, you're saying that we remove?
Yeah.
So current path dot
Remove.
remove.
But when you remove at line
It's-
27, what happens to line 20? Because
Yeah, they're also ready to remove. Yes, I was waiting for this line to finish. Yes.
Okay, so we remove the final element.
Yes.
Okay, so that will
Current path size -1. Size.
Yeah, I just started using Java.
You used to use Python, right?
Yeah, I just made the switch. So
Python is very short code. I think you can use it for interviews.
We can do same thing at the line 20. Yes, also before returning.
okay.
But that is a leaf node, right? What we need?
We
So-
added leaf node, but when we go up and then when we
Oh,
go
okay,
to right
okay.
tag,
Yeah,
we
yeah, yeah.
don't want
Yeah,
that.
Yes, yes. Yeah.
So
So
when you're removing it
So-
from the current path is added to the output. So it's by ref, right? So the output doesn't change when you're removing something from current path.
I think it should be cloned when we are adding
Yeah,
it
I
to
think we should.
output.
Yeah, correct.
Clone
It
that.
should be cloned. You have to say, yeah.
maybe try this. Okay, so it compiles and it works in the first test case. Yeah, way faster.
Yeah.
Cool, awesome.
Good
Yeah, that was
improvement.
actually I initially tried just passing current path, but I didn't realize you have to remove elements. Okay, cool. Anyone have any questions on so far on what we've done?
Yeah, in this approach, actually, I had the current path adding the root.val after the if statement, and it was going out of bounds. And it does make sense. I mean, it does matter if we add it first and then check. Just to mention that if you change the current path dot add a root.val after the if statement,
Okay.
yeah, you're gonna go index out of bounds. I'm just saying
Which
Oh, okay, okay.
it matters.
Mhm.
So line 17, if you move it to line 24,
okay, then
yeah, you're gonna get index out of bounds.
got it.
Yeah. Cool.
Okay. I think-
Thanks for the enhancement.
Yeah. So one more follow up on this one. I don't want to spend too much time, but okay, so let's say now in all of these so far, we've only been considering paths from the root to the leaf. Now, what if the path doesn't need to start at a root or a leaf, but it's still like a downward path? So you can't have a path from like 13 to 8 to 4, but you could have, for example, 8 to 4 if the target is 12. And we want to return either true or false, like in path sum 1. Any thoughts?
So it is still path, but then path can start and stop at any
node.
point, right?
Yeah,
Any
so
node.
we don't check for that leaf in the if statement, correct?
Yeah, we don't check for the leaf.
Yeah, but there is another thing because it can start from 4 also. So
Yes.
the current method is not definitely going to work as it is.
Yes. So yeah, so the current method, like the ways that we've been doing, it's always rooted at the root node, but the path can essentially start at any node in the tree. So
Yeah.
So
Should I-
for that, maybe the contiguous array approach can be used, where we keep the current sum, getting basically we carry the current sum along when we are traversing the path, and whenever we have a new current sum value, we keep updating the number of occurrences of the current sum. So the target, so whenever, suppose we have current sum y, and if you want to check whether we have met the target, so y minus the target, if suppose it comes x, and if we have any node where there was x, it means there is a path, otherwise not.
yeah, so is your approach, are you saying it's like similar to the prefix array sum problem, if you're familiar with that?
Probably I'm not sure about prefix array, but we had a session where there were a couple of problems for contiguous array were discussed, where yeah.
Right. Yeah. So, yeah, I think you're correct if I understand what you're saying. So first, I guess I'll just show my code. So this code works, but it's definitely not the most efficient way, because essentially what I'm doing, I mean, this part is pretty similar to the helper that we've seen so far. And then in the actual method, I'm calling the helper with the root, and then I'm also calling the same method again on root.left and root.right. So essentially it's considering like 10 as the root with this call, and then I consider each child as like a separate root when I call path sum of root.left and path sum of root.right. So it's going to traverse the whole tree for 10, and then also again for 5 and 3 and all of its children, and so on with 3 and 2. And so I think, so does everyone, like, is this part at least clear? This solution?
Yeah.
Pretty similar to 1. Basically, we're just adding this additional, we're calling it on the child nodes as well. And like Martino said, we're not checking for a leaf node in the helper function here. But you could see that if you do it this way, it will, you have a bunch of repeated work. Because first, like in this call, you're going to traverse the whole tree just for the root 10. And then when you make this call, you'll do it again for 5 and all of its children, and then same with -3. So I think what, so who was talking about the array solution?
That was Anirudh.
Yeah, so I think that's something like that would probably work. Something that's like similar to a prefix sum array type of problem.
So what would be the time complexity of this?
This one, in the worst case, I believe it would be n squared.
We are calling almost like 3 times.
So like consider if the tree is like a linked list.
Mhm.
So you have like
Finding every possible combination of numbers, right? This is
right. So first, traverse the whole list for Mr. A with this call. Now when you make this call, depending on whether like which node is called, one of these two will traverse the whole list again, starting from B. And then similarly, like it'll keep going down the tree. So I think it's n squared for the worst case. If it's a balanced tree, because I know then as a comment. All right, so yeah, so if it's a balanced tree, then we explore all paths like from the children in it, and then yeah, so like we balanced tree, then each child would have half of the number of children, like on So then you get like some sort of a summation like this. And I believe it works also on log n. But that's, of course, that's the best case where the tree is bound. The worst case is actually like a little bit easier to think about. Like this case where it ends up being installed. All right. Any last questions on this like path sum variation before we move on to the next thing? Okay. All right, so this is actually a binary search tree problem. Let me go back to this view. Can everyone see this all right?
Yes.
Yes.
Yeah, so it's an iterator question. Basically just design an iterator for a binary search tree. So every time you call next on the iterator, it'll be doing like an in-order traversal of the BST. Anyone have any ideas on how we might approach this one?
Can I actually ask you a question? Because I didn't understand how the next function works in terms of like, at the first, I can see that it starts from the root and like next is probably like supposed to be the like next smallest value. But then when it is like, then how does it become 7 is kind of a question for me.
Yeah, sure. So like if you have a binary search tree and you do an in-order traversal, so like an in-order traversal is where you process the right child, then the current node, and then the left node.
Left and left root and right. It's basically the sorted order. Yeah, ascending.
Increasing.
Increasing order. Yeah, sorted. Yeah.
It'll give you the sorted sequence of elements in the tree.
Okay. So for any given like input, you can still assume that like I am going to iterate through this in-order traversal.
Yeah, so the iterator is like taking care of the in-order traversal behind the scenes.
Okay.
If you're consuming the iterator, I guess that's you'll just expect to get the elements in the correct order.
Okay.
But behind the scenes, it's like doing a in-order traversal of the BST.
Okay, now I see that. Okay, yeah, it makes sense. Thank you.
Sure. Yeah.
Yeah, I have an idea for this.
Yeah.
So I'm thinking like to take a stack.
Okay.
And first of all, traverse the left. Like till we need to traverse all the left part, like here, the root. Here when we are on a route, we'll be traversing to the left, and when we reach at the end of the left, then we'll start like side by side. We'll be putting that in a stack, and so the topmost at the topmost of our stack, we'll be having the node which is at the leftmost point.
Right.
And so whenever we call the next, then we'll pop that stack, and along with it, we'll check that if that node has right, then we need to put all the elements of the right. Like I'm assuming I'll be taking a one function where I put all the elements on the right in a stack and just return that node. So that way.
Is it like rights or rights left?
Yeah, so right, left. Yeah, correct.
Yeah. Mhm.
Yeah, sorry. Yeah. So I'll be putting the, I'll be going to the right node and put all the left nodes of that. Yeah.
Yep. Exactly.
Yeah.
Yeah. Do you want to write code for this?
Yeah. So.
Yeah. So either you could share your screen or like you could use mine. I'm not sure if, I guess that we could try that again to see if it works.
Yeah, I can write in Python. So.
Okay, sure.
Your screen as well. So if you have Python.
I should. I was having some problems with my Python as of recently. Let's try.
So do you want me to share my screen or?
Either way. I could like create a Python file for you, or you can.
Okay. So how can I write?
Yeah, I guess we should probably test that first because it actually didn't work last time. So it's Sonia, right?
Yes.
Yeah, it should. I think it has access. So it's okay. So it's waiting for Sonia to control your screen.
You need to click the lock to make changes. Last one, which you have open, security and privacy.
Right.
Write your password, and then I think you can unlock that.
Yeah. So it's selected. I think it should.
You want to select the Zoom one as well?
Oh, sorry. Yeah. This is the reason I was thinking that. Yeah. Okay, so I selected that. I can, I guess, lock this again. And then, are you able to control it now?
No. So you need to give me permission or like.
Let's just try it again. It says you're controlling. Actually, it says waiting for Sonia to control.
Yeah, let me.
Okay, I think that's you, right?
I'm not able to write it down. So, yeah, yeah. Is it writing?
Yeah, that's you.
Yeah, I'm writing.
So yeah, let me just save this as a Python file real quick.
Okay.
Yeah, all yours.
Okay, thank you. Let me check. Okay. So I'm assuming we have BSD Iterator. In lead code, it's written like this. So I'm writing like this. So I'll be taking one stack. And I'll create one function which is find left and passing root. Sorry, I haven't created the function.
I like your theme, VS Code. It's pretty clean.
Yeah, I actually don't use it that much these days.
Somehow when I write it slow, so bear with me. So I'll be creating a left function where so until unless it root has left, then I'll be putting that in a stack. It's by default, no. So one thing more, shall I create the class of the tree node, like left, right?
Yeah, I guess you probably should, yeah.
Or I think we can assume it's there.
I mean, just for the, like, otherwise it'll keep saying you have an error, like unrecognized. It should only be a couple lines. If you want, we can like copy and paste the given one.
Lead code, yeah.
Yeah, that would be great.
Yeah. Let's see. So switch to Python or Python 3.
Python 2 or 3, it's fine. 3 is fine, yeah.
Okay, cool. I don't have a solution for that one.
You can just copy that tree node class. That would be fine, just.
Yeah. Yeah, and of course the indentation is different than the editor. It's kind of the annoying thing about Python is that indentation is always matters.
Yeah.
Okay, hopefully that now.
So yeah, it's Python 3. So let me change this thing. I don't need an object over here.
And if you want, you could also take the same like method signatures as the example, because I think the constructor might take root.
I have opened in my screen, so I'll be doing that.
Okay, cool.
Yep. So next, sorry. Next. Let's take, I'll be popping the node from the stack. And while node dot, sorry, if do not do right, not yeah, I have already created that function which will traverse that all the nodes in the left hand side. If node dot right, then I'll be calling the function of find left and pass the node dot right to put all the nodes which are on the left hand side in a stack, and then I'll be returning the node dot well.
Can I ask you a question, Sonia? Yeah. So in the question, it says that like if you call iterator.next, it doesn't seem to have like any parameters. But if you have paths and self, can you actually call it without the self itself?
Yeah, so in Python, like methods in a class always have self as the first argument.
Okay, gotcha. Okay.
I think it's as good as in Java, it's this. So it's pass of it is a way of telling like this, like use this reference here.
Okay, sounds good.
Yeah.
So it is for calling the functions, and it is required to have in Python. So next is has next. It's just return if the stack length of stack is, sorry, self.stack is greater than 0.
It's like not empty, right?
Sorry?
Is it equivalent to not empty? Yeah, okay.
Yeah, exactly.
It is greater than 0.
Yes, yes.
So I think we need to pass the root, so that's why it is giving an error.
Yeah, let's just.
I just have to pass the root of.
Yeah.
Yep. Still, it's giving the error. Oh, so it's saying undefined variable.
No, I think it's gone now.
Oh, okay.
Yeah, I think this should work. Do you want to just try pasting this in the lead code and see if it works?
Yeah, you can try it in a lead code.
Okay. I guess I'll just get rid of all this. Yeah, so yeah, the constructor takes root. Okay. Let's see if it runs. Okay, so we passed the first test case. Let's see if it passes all the test cases. Yep.
Somehow Python is always take time. I don't know why.
Python is always what?
It's always take 18 seconds. So it's
Yeah, compared to Java, it's like taking more time. Yeah.
Java takes longer.
Can you explain the logic of the solution again?
Yeah. So basically, anytime you, let's pull up the problem again. So we have this BST, and basically what we want to do is an in-order traversal of this BST. But if we just did a recursive in-order traversal, there's no way we could like pause in the middle, because we essentially have to pause and then only return whatever the next value is. So we're not doing like a full in-order traversal like every time. We're like starting with 3, which is the leftmost element in the tree. And then we return that one next is called, and then in the stack, the next thing will be 7. Because if you, let's see, you visualize the stack. So essentially the idea is that we're doing an iterative in-order traversal instead of a recursive one. Because if you do a recursive one, there's no way to terminate until you hit like a base case or some terminating condition. Like the way I think of it is, it's like you're tipping over a domino and then there's like no way to stop the rest of the dominoes from falling if you do it recursively. If you do it iteratively with the stack, then like you could pause at each step and only return whatever you need from the next call. So what we're doing is, like, if you visualize the stack, the first thing we do is we call this find left function, which it starts at the root that you pass, and then it traverses the tree. It'll first add that root to the stack, and then it'll go to that root's left child. So if you visualize it on this tree, first it'll have 7 and then 3. And then let's do this in a... Right, so this is our stack so far, where 3 is at the top of the stack. So the first time we call next, node equals stack.pop, that'll be 3. So we pop the stack. And then if that node has any right children, then we add those. But in this case, the node is 3. 3 is a leaf node, so it does not have any right children. So we just return node.val, which is 3. And our stack still has 7. So then when we call next again, again, our node is now 7. We pop the stack. 7 does have right children. So we add 15, and then we essentially do the same thing starting with 15. We go all the way to the left. And the reason we go all the way to the left is that like that's what gives you the correct ordering in a binary search tree, since the left child is always less than the root. So you'll add 15, and then you'll add 9. So then you call next again. That'll return the 9. 9 has no right children. You call next again. So now the node is 15. 15 does have a right child, which is 20. So 15 is popped, and then you add 20. And then once again, you call next, and then you return 20. And at that point, you're done.
Okay, thank you.
Sure.
I really like the solution. It's beautiful.
Yeah. I like iterator problems in general.
This question also comes with one more variation, that if you can't take extra memory.
I think that will be solved using
The Morris traversal. Then we have to use that. So
sorry, Asim, I missed that. What traversal?
Morris traversal. So that use the tree itself to do this in-order traversal. No extra memory is involved. So that generally comes as a follow-up question to this one.
So do you want to explain that?
I can explain that.
Do you want to share the screen or?
Here, let me share my screen.
Okay.
I will share the whiteboard. Know when you can see my screen.
Yeah, I can see.
Okay. So, what Morris traversal says, like, let's take an example of a tree. We have 3, then we have, let's say we have 4 here, then we have 5, then we go this side, let's say 15, 9, something like this. Okay, so we have a tree. Okay, so let's make this as 1. So it should be a binary search tree only. Okay, so what Morris traversal says that when I'm here, if I can, so right now the problem with this in-order traversal is that if we are doing like iterator, we need to find a way to come back. So if I'm going from 7 to 3 to 4, then I should be knowing, like, after that 4, I should be doing 3 and 5. So I need some way to store a reference. So while coming back, I should be knowing where should I go. Right now, how the stack helps, like we always keep this 7, 3, 1 in the stack. So while coming back, we know like where I have to come. So after 1, I have to come back to 3. From 3, I have to come back to 7. But if I don't have anything, then how I'll solve that? So is that part clear?
Yep.
Yeah.
So if I have a stack, then I don't know after 1 where is 3, because I already passed from 7, 3, 1. So that was one thing. So I need to find a way to store a reference. So what Morris traversal says, like, if I can store this as a right side of my predecessor. For example, 7's predecessor is 5. And 5, there's no right to 5. So if I keep 7 right to 5, so I'm storing my reference and that I can use later to point it back to 7. So how it works, that when I'm here at 7, I look for my predecessor, and how I can find my predecessor would be off my left and then going right. Correct? So what is 7's predecessor here? 5. Is that clear? So there
Yes.
we make a reference back to 7.
So is it basically the closest value to the left to the root on the left side of the root?
To the left side of the node. So,
okay.
So it's a predecessor of 5. 7 is 5.
Mm-hmm.
And if it is not a binary search tree, then still we have to do something similar only. Like, and because his 7's predecessor will always be like, if I go to left and then go right, that would be 7's predecessor. I'm just making generalize. If it is not a binary search tree, still the same algorithm will work.
Okay.
After that, what I will do, I will go to 3. So for 3 also, I'll do the same thing. What is 3's predecessor? It is 1. So I'll go to 1. And 1 does not have anything, right? So I will make a link like this.
Mm-hmm.
From 3, I will go to 1. Now 1 does not have any left. So this is one point where I can do some action. Where I don't have any, so where I don't have anything. So I will make 1. So 1, I can print 1 here. So where I don't have any left, there I can take an action and print 1 here.
Mm-hmm.
So after that, next time what I have to do, I have to, okay, so I was having something like a current. Earlier the current was 7, then 3. Now, now when 1 does not have a left, I will print 1 and the current will become 1's right. And right now at 1's right, what is there? 3.
3. Yeah.
So now we again came back at this position. So now there is again the algorithm will go into the same process. It will go its left and try to find its predecessor. So it will go 3, it will go 1 and try and again go right. If you see, this will become a cycle. But if I make some condition, if I find this guy itself on the right side, that means I have already traversed this path. So basically 3 will go to 1, 1 will say on my right is 3, and these 2 guys will match, and then that means it's this path have already done. Like for example, 1 is already done. And then I'll take another action where I'll break this path. And make my current is 3's, and then I'll make my current is 3's right, which will become 5.
And you process 3 also, like, so you can print 3 because.
Yeah, I have to print 3 also, yeah, before that. Yeah, correct. Thank you.
So you're only modifying the right pointer?
Yes. So from 5, again, there is from 5 there is no left. So I can print 5 and make my current as 5's right, which is 7. So again, this process will start. 7 will go to 3, 3 will go to 5, 5 will go to its right, and 7 match. So it's a time where I can break this guy and print 7, and I'm done with this left side. And now my current will become 15. Is that clear till now, or I can repeat?
Yeah, it's clear.
The current value will keep on checking only the right branch of the BSC tree. Is my understanding correct?
No, there are different. When I'll show the code, might be it is more clear, but there are different conditions. First condition is I'll check if my current left is null, so I can print my current. So first condition is current left. Oh, I can't write here. Null. So this is first condition. I can make a print. Then if and make current dot right is equal. Okay, make current equal to current dot right.
You can use a test box if you want to.
Sorry.
You can use a test box. I will like there's an option to insert a test box.
Yeah. So first check is current dot left is equal to null. Then print current and make current equal to current dot right. So this is our first condition. Then otherwise I will go to I'll find predecessor of current. So try to find predecessor of current, and so now there are two subconditions. If current itself found as part of predecessor, then that means what I can do is print current and make current equal to current dot right. Otherwise, I will do that step where I told like if I in the other thing where I already found like 5. If you see that example from 7, how I've 7 5, I have to make a connection between predecessor dot right equal to current. So these things I'm doing right now.
Okay.
After this, then we need to go to the left side, I suppose.
And current equal to current dot left, because anyhow I have to go towards 3, 1 and other things. If this is clear, then only we'll able to proceed. It's a little tricky algorithm. What I felt like if I have not seen this and I didn't learn by heart, I always forget this.
So essentially, Morse traversal gives you a constant space traversal of a constant space iterative traversal of a BST.
Yes, constant space. But if you see, my traversal became really lengthy. If you see, I from 7 I went to 3 to 1 to 5 again. I went back to 7. So if you see, I'm again repeating the same process again and again. My space became constant, but my runtime became almost like Gravel, because I'm processing that same node couple of times, like 2 times at least.
Got it. Yeah, cool. I never knew about that.
If you want, I can share my code also.
Yeah, please.
I think you can move to the right side, with the right half of the tree.
Yeah, just complete the example like.
Okay, so we were at 15. So from 15, I have to find the predecessor. So 15 right is not null. So I have to go to step 2, find the predecessor. I went 9. From 9, I went towards right. I couldn't find. I found null. So that means I can make a connection between 9 and 15, and now my current will become 9. From 9, there is no left, so that means I can print 9 here and make my current again as 15. If you see step in step 1, from 15 again I will go towards 9. I try to find right side. I found myself only. It's step 2, 2A. So first I will all break this connection. I'm forget to mention the 2A step, and then make current as first also print 15, and then make current as 20. So 20 is there is no left. I can print 20 and there's no right. So this is done. But as part of the solution, because this is like a next has next another thing, I have to also pause it. If let's assume this was a question where I have to only do in order without extra space, I could have just done in a while loop. But here I have to also pause it. So then there is one extra conditions to just pause this iteration till we resume it next time.
So we can just store the current pointer and then see if the current is not null, then we have next element.
Yes. So if this is clear, I can show the code and then we can proceed further.
Yeah, go ahead.
Yeah, please let me know when you can see my screen.
Yep.
Okay, so we have this next and has next. If my current is null, that means I don't have anything next in my thing. So that is one condition. I'll take another variable current in the beginning. And then what I'll do, initially I will assign this current equal to root. And then if somebody call next, this will keep on going while current is not equal to null. And so this was our first condition. You remember step 1. If current is equal to null, I have also created temporary variable result. Result will become current. Current will become current equal to right. And I can just break and return the result.value. Let's say there was something on the left hand side. I will find the predecessor of current, which would be the left node of left of rights, which would be in the left, and then we have to go towards right. So I'll keep on going towards right while temp.right not equal to null, or temp.right also not become current. This was our other condition where I should not find myself. And after that, this is just to find the predecessor.
In which case that you can find yourself?
This one.
Yeah, but as an example, so while you're iterating, how can you become end up looking at yourself?
Yeah, so let's assume this condition is not there. We are doing for the first time.
Okay.
And we are finding the predecessor. At some point, my temp.right will become null, correct? Okay. Then if it is null, what I'll say, my temp.right is equal to current.
Oh, okay, okay.
It will become current.left.
Mm-hmm.
Then this was and then we'll keep on going towards left till we find current dot left equal to null, and then print or return whatever.
Okay.
I can even return from here. I don't need to break also. So other condition is when my current dot when I have printed this, my current will become current dot right. Let's assume this became the same path again. I can't do both whiteboard and this together, otherwise I could have showed. Or let's do this thing. Okay, so now I'm this condition where again I reach back to 7. So when I come here, this time I will hit this guy.
Gotcha. Yeah.
And that time my temp dot right is not null. I will come to this condition. My result will become temp dot right. My temp, I have to break this guy. And current will become whatever the results right, and then just break it.
Okay. Okay.
If this was just in order thing, then I don't need to do all these things. I don't need break conditions here. I just need a print here or something, whatever. I just have to print result. That's it. So print result will happen here and here. If it's not, it's has to go in one single pass only. Same logic, this same while loop, no need to break, just keep on printing. But the print will happen here and here. I will recommend go read. There are, I think, some examples on Geek for Geek, which explains more better, like what I have explained. And I think there is if I have to do pre-order also, I have to just tweak some conditions here. I can even do pre-order without using extra space.
Nice. Yeah, thank you for sharing that.
Yeah. So Gaurav is asking, is that clear?
Yep, it's clear.
Yeah.
Okay. Any last questions before we move to the last problem? All right. Okay. Whoops, I don't want to show that just yet. Okay, so last one. My screen is visible, right?
Yeah.
All right. Yeah, so finally, this one is called binary tree right side view. So yeah, basically given a binary tree, it's like, imagine that you're standing here on the right side, and you want to return a list of the nodes that you would see standing from the right side. So in this case, it's obviously like all the 3 right nodes, but like let's say if this 4 was not here and it had some other left child at 3, then that would be in the output in place of 4. That makes sense. Is the problem clear to everyone?
So what if 4 is not there? What should be the answer?
Yeah, so if 4 is not there, then it would be 1, 3, 5.
5, 1, 3, 5.
Yeah.
If 3 and 4 both are not there, then it's like 1 to 5.
Yeah.
Okay.
So essentially, like you could think of it as the rightmost element at every level of the tree.
Okay.
Then I guess you would check length of left side and the right side. And for the parts that right side's length is covered, you get the right nodes, rightmost slope and nodes. And for the other parts that is left side that is extending the right side's nodes, you will get the rightmost nodes from there.
Yeah.
If left height is more, then it's like right nodes plus whatever the extra nodes on the left side, right?
Correct.
So I think think in this way. If you are doing a level order traversal, whatever is the last node in your level is your answer.
Yeah, exactly. That's how I thought of it too.
Yeah. So how we can store those values? Like if we follow this, I think it would be a depth first search.
Yeah.
So we can do a level order itself.
Level order traversal. Oh, okay.
Whenever when we are done with one level, we can find what is the last guy in that node and put it in our answer. That is one way of doing. So, and other ways also using recursion, where you pass your level in the next like in the next call, and do something like a post order traversal, and there is a guarantee that we can do something like a post where
I
you.
think for pre like post order.
So it would be I will say visit node, visit right, and visit left.
Then it's a reverse post order. No, reverse pre-order. No. Yep.
No, it is visit node, visit right, visit left. So it will be, I don't know which order. But before that, level order traversal is clear to everyone.
Yes, but we need to use space, right, for that? I mean,
Yeah.
like some storage. Yeah.
Yeah, we need a queue. It is as good as your breakfast search, but we also delimit kind of a delimiter that which will tell, okay, this level is done.
Mm-hmm.
And, and if I'm doing a recursion solution, again the space will be needed because it is taking inbuilt space. But the thing which I'm trying to say is that we can do using some kind of order also, like I mentioned, visit node, visit right, and visit left.
Yeah, I think the level order traversal is probably like the most intuitive way of thinking about it, at least to me.
Yeah.
Would you want to write the code for that, Asim?
Sure. But I think doing the recursive approach will be a really compact solution.
Okay, yeah, whatever way you want to do it.
Okay.
Yeah.
So you want me to share my screen?
Yeah, if you want, or you could use mine either way.
I can share my screen. Sorry. Okay. Let me know if you can see my screen.
Yep.
So I will try something like recursive, because I'm pretty much sure many people can do level order traversal and can be done easily using level order traversal. So, but thinking about a recursive solution is tricky here, and then the solution you can even use for other places also. So I will create a tree node rule int level, and then For this, let's do a whiteboard first. Can I clear this? Okay, clear all. Okay. Okay, so we have 1, we have 2, we have 3, we have 5. Oh, 5 not here. Five, and we have 4 here. So what I'm proposing is if I come up with some kind of traversal where I can where I can find a way which will give my answer the way I need it, then I think I'm good. So starting from 1. So yeah, I know 1 is my answer. And if I take a list here, and this is my 0 index, this is 1, this is 2, this is 3, this is 4. Okay, so what should be next? So next should be 3. So basically what I'm saying, like I will go from 1 to the right and also increase my level. So from here I went to 1. My level became, here the level was 0. Here it became 1. So here I don't have any, if you go 1, there is no answer there. So I can go and easily put 3 here. From here, from 3, I will go to 4. And I pass this level 2. And here also 2, there is nothing. So I can put 4 here. And from 4, I can't go towards left and right. And from 1, then I will go to 2. Again, I pass my level as 1. But already something is sitting there. So I can't do anything. From 2, I will go to left, I can't go. Right, I can go. I will pass 2. But at 2, there's already 4. So I can't put anything here. And then I have to return this answer.
So from two, like you will go to the right first.
No, yeah, from 2 first I'll go to right first, yeah. And then I go to left.
The trick is we start with the right first and then go to the left, right?
Yeah,
always. Yeah.
The trick is visit node and then visit right and visit left. When we are visiting node, then we have to also see and when I'm visiting node, and check if I have registered and val for that level. This is step 1, this is step 2, and this is step 3.
So I have one question. If as per this algorithm, if 3 was not there, so means if from root we go right and level 1, but 3 was not there, right?
Do this.
So in this case, in the queue, what will be add? We will go to the left, right? 2.
1 to 5, yeah.
So like in this list, 0th will be the 0th level and that node, right? And first will be the first level and that node.
It is like what we have seen for the first time when we reach that level. So for example, from 1, I can't go right. So I'll go this side. I will pass in one more level. Here, I have not seen anything yet. So I'll put 2 here. From here, I will go towards pass 2. I have not seen anything here yet. So I'll pass. Let's say it was having 4 here. From 2, I'll go towards again pass 2. But I have already seen something there. So I won't change it. Is that clear?
Yeah, thanks.
I was thinking it's like we are storing that node as a index as a level. So it would be a unique every time that particular index like at particular level.
Mm-hmm.
So can we use a map as well over there so that like, whenever we
Yeah, we can use a map. We just need to find a way, like I have registered something for that or not. The reason I've used list because the
We
expected
need to
answer,
maintain the order, right? With the map, it's difficult to keep an order.
we can still maintain the order. In map, I will put like at level 0, I have seen 1. At
Oh, okay. Yeah.
level 2. At level
Yeah,
2,
we can do that. But
if it is not ordered also, it will go like this. And then I know what is the length of my map. It is 3.
yeah, accordingly we can loop and get the
I
answers.
can
Yeah.
do 0, 1, and 2. Put that back in my list. It will become 1, 1, 2, 5. Resultant answer is a list.
Yes.
So either way, we can even put in a map. So I used a list because
We can directly set in the index, right? Yeah.
And it is a dynamic thing, so it can keep on increasing based on the height of the tree.
So the one thing which I am focusing on a map because here we will not remember to go for first of all right or not remember or something like we'll start with the left and then right always. So for map, if we are traversing, then whatever is the at the right, whatever will be the last position or the last value, it will automatically get updated at that particular index of a map.
No, we don't want to update anything. We only want to add if it is not there.
I believe like Sonia is suggesting an alternate approach where you do the pre-order traversal current, left and right. And if you already find a value at that index, you update that.
Yeah.
I got it. So, I got it. So that is another approach to see this thing. That do the similar thing. So at level 0, I have seen 1, and from there now you can do any traversal. You can do a pre-order. You can go to here. You say, okay, I saw at level 1, 2. Let's say we have 3 also. And then from there, I went 4. As I told, at level 2, I saw 4. And this time we are doing a pre-order traversal. And from here, I went towards 5. Oh, I saw, 2 already. It's override this, whatever you have seen for the last time. And from here, when you go this side, we put 3 here. So basically what we are doing here is whatever we have seen for the last time, we are just keeping that in the map.
I have a question. How to check the index 1 is used or not?
No, we don't.
What's the
just keep on overwriting it. That's it.
We just overwriting that index.
If it is not there, create it. Otherwise, overwrite it.
Yeah, I think you
but
can.
How to check it's visit it's already visit index 1 when you try the right subtree. Yeah, because maybe you initialize the whole array with 0 element.
So this is we are discussing a different approach now. So now we are discussing.
Okay.
So first one is doing. First approach was. So first approach was like I mentioned here. So second approach which we are telling do
So just to like add here, even when we are using the array, it's a dynamic array. So you won't like initialize the array with 5 nodes or something.
Yeah.
It's a array list. So if you find that if the size of the array is less than the label that you are visiting, then you add it.
Yeah. So basically, okay, we are again switching gears. So I'm again going back to the previous approach. So where we were not having anything in our array. And so initially in this list, we don't have anything. So so the list is empty. So at position 0, I put 1. From there, I went to 3. And so size of this array is still 1. So basically, at another thing, I can put 3 here. From there, I went 2. I won't put 2 because already this is at level 1 or 1, or think in that way. We have started from 1 only. At level 1, we went to level 2. Here also, we went to level 2. Already the size of the array is 2. So that means we already have answer for that level. Is that clear? I don't know who asked that question.
My approach is to do the BFS from the root. Just create a queue and put the root into the queue. When you traversal the level 0, and the next level, you pump to pump front of the queue and put its left right into that queue and traversal the whole tree till the leaf node. And when you traversal each level, you just put the last index of element to your result array.
So I think that is the initial approach which we have discussed, and that is I think the straightforward approach to think, doing a level order traversal and be done. But if we are discussing, if the interviewer asks that, hey, you can't use extra space like queue recursion, but recursion is fine.
Okay. Yeah.
Then we can't do that thing. And this is more compact code if you are doing a level order traversal. That is another advantage of doing in this way. And if I have to do left side of the view, I have to just change the conditions. Instead of visiting right, first visit left.
Yep. So do you have code for this, Asim?
Yes. Let me. Okay.
Can you reduce the font size a little bit?
Okay, so this is a solution. Okay, that doesn't work. Sorry. Let me share my screen. Okay, so this is the solution which I was discussing. You take a list. If you're in start from 0, if your size is similar like that, then just put it there and go towards keep on increasing your level.
Sorry, can you explain the logic behind this code?
So, so this is similar to what we have discussed. So when I'm at 1, my list is empty. I will put 1 here. Then from 1, I have to go towards right and put level. So what I'm doing, I'm going towards 3 and putting level 1. My list size is equal to my level, which is 1, if you see. And then I'll put 3 here. Then from 3, I will go towards 4 and put level 2. Here it is again, 2 is equal to size. I'll put 2 here. From 4, I can't go left and right. Again, it will go back to 3. 3 does not have
You
left.
put like 4 in the list instead of 2. Like you should.
Yeah, sorry. And from 4, I can't go left and right. From 3, I can't go left. From 1, I can go towards right. So that time now I am this position. I'll pass 2 and 2. 2 and 1. So, but my list size is already, you see, 3. So I can't do anything here. From 2, I will go towards 5 and pass 2. Again, the list size is already 3. I can't do anything. And then I'm done. So what I will return 1, 3, 4 as my answer. And if you see, this code is really compact as compared to level order traversal, where I have to take a queue, have to maintain the level information, take its last value of the level, and like that.
Yeah, this is really like nice, a really nice solution. Anyone have any questions? Last questions?
So what are the follow-up questions on that? What if you have to do the left side view?
So we need to switch gears. We just need to do. So this will become the left side view of the tree.
It'll be 1 to 5.
Yes.
What if you have to do the top side of the tree, top side view? What should be a top side view?
Top side view should be, I think, 1, 2, and
like starting from left to right.
I think 2, 1, 3, 4, right? Or
2, 1, 3,
4. Is that correct? Top view.
So maybe left, then the root node, and then the right.
Yes.
So I don't actually understand the top side view. Like, what? How are you visualizing that?
You can visualize it like let's say you have 1, okay, and then you have 2 on the left, okay, and then you have 5 on the right. So if you see 5 is coming below 1,
right?
Okay, so that's how. Let's say like 3 as a left element.
3 as a right, right?
No, but let's say like if 3 as a left element. I'm just like assuming like let's say 3 as a left element, then 1, 3's left element, and 5's and then 5. They will be like on the same vertical line. Okay, so you can think of like vertical line. 1 and 5 are on the same vertical line. If 3 as a left child, then 1, 3's left child, and 5 are on the same vertical line.
Yeah.
Okay.
Makes sense.
So you can, in that case, like the top side view should be 2, 1, 3, 4. But those are like again like the variations of the same problem.
Yeah, this is a very concise solution. Yeah, it's a great solution.
Okay, I think on the top side view, we need to take care of a couple of things if we have seen something.
Sorry, so what was actually what would be the top side view of this example?
2, 1, 3, 4. 5 is beneath 1, if you see.
Right, okay, so like the 5 is covered.
We need to see, can you check if LeetCode has this top side view question in the problems?
Don't know.
I don't think like the lead code has it, but let's discuss the solution, like what you should do for the top side view.
Just the outer. What I feel is maybe we need to capture all the vertical positions and see which are all on the top is obviously only one, which will be the root, but whichever the leftmost and rightmost in each level.
Okay. So you start with 1, okay, and let's say that vertical line starts with 0. When you go to 2, you pass -1, and if you go right, you pass +1.
Yes. Okay.
Can we do that?
Yeah.
And then like use a map or whatever to keep the indexes if you have already seen that index. So
add to that. Yeah.
So it should be the same concepts, but here you have to pass minus, like keep passing -1 on the left, +1 on the right.
So I think what Gaurav is telling, like -1, and instead of this,
it'll be a map. Yeah.
It will be a map. It will just be map dot put
level. You need to add, get and add, I think, like get or diff.
Yeah, if map doesn't contain that, it should not be like label. Let's like not call it level, but like left or right, whatever you want to call it, because it's technically like not a level. Okay, sequence, you can call it sequence, and if that sequence is not present in the map, then only you put it.
No, is the sequence can repeat?
Yes, because
it can have multiple values, right?
Yes, because if you see the 1 has vertical level 0, then if you go 2 has vertical level -1. Then if you go to 5, then 5 also have vertical level 0.
Okay.
Because from 2 when you are going to 5, you are passing +1, and 2's vertical level is -1, so 5 vertical level will become 0.
And how 0 will come again?
You start with 1. What's the vertical level of 1?
0.
0. You go to 2, like on the left. What's the vertical level of 2?
Got it. Yeah.
-1, and then you go to 5. Yeah.
Because 1 and 5 are at the same, what is longitude or latitude, whatever.
Right. So just to be clear, so the final output, you only have like a single, the first value that you hit at each horizontal level, right?
First and last, it will be both, right? The last will be the rightmost. I mean, like on the rightmost branch, which is 3.
Yeah, I don't mean level actually. Like I guess sequence is what we're calling.
Oh yeah. Okay. Yeah. Correct.
It will be on a like 1, 5 is in a vertical. So this is.
So it could be a list of integers. Sim, I think map in the value, and then we finally select.
No, we'll only keep one value, right?
As an answer.
Because we are going like left or right and giving different coordinates.
Oh, okay.
So I have one question. For 3, it will be 1, right? Vertical view.
Yeah, 1.
Then for the map, okay, for 3, 1, and for 4 is 2, right?
Yes. So let's see. So when I start my sequence 0, I put 1. From there, I went towards -1. I put 2. Then from there, I went again left. Nothing is there. I went right where my sequence becomes 0, but 0 we have already recorded, so we won't do anything. So left side is done. We go towards right. We give 1, 3, and from 1, from there I will go towards left. Nothing is there. I go towards right. Give 2 and give like 4, and yeah. And I can create this as a tree map. So,
but in this case, if instead of 4, the 3 has a right child of 4, right? So if it was not there and 3 had a left child, so in as per your, the second level will be that value, right?
So what we are discussing here is
Just if you remove the 3 to 4,
you're telling like
just remove that 4 and just make it here on the left side.
Yeah, it won't happen then.
Then it won't work, right?
No, it will work. From 3, if I go towards right, what will be my value? Value will be 1, right?
Oh, okay.
And
Okay,
I have
got it.
from 1 it will become 0. Sorry. So 1 and 7 are kind of like the same.
Yeah, it is already covered. Yes.
Yeah. And I can make it as a tree map. So I will get all of them in kind of a
order. Yeah.
Order 2, 1.
Thank you.
And tree map is like an ordered dictionary, sort of, right?
So here I don't know, like -1, 0, what sequence could be there. I only know the length, but it could be really random, what I'm thinking. Or it could be, yeah. But I don't know where to start.
So as we were saying that 3 is on a left hand side, which is 7. So 5 and 7 both will be at the same position,
Kind of.
but it will not be possible, or it's possible.
Not possible.
But like they won't be in the answer anyway, right?
Because if you take a look
They're
at
not visible from the top. Yeah.
Yeah. So if you take a look from the top, both 5 and 7 are hidden.
Yeah.
It doesn't matter like if 5 is above 7 or 7 is above 5. Okay, that's like irrelevant to this question.
Okay.
So, but if we had a bottom side, then in that case, 5 and 7 would have been some controversy there.
Yes. And now it's an interesting question because like bottom side view, I've seen that question too. If you're traversing from left first, then 5 will be hidden by 7. But if you're traversing the right first, then 7 will be hidden by 5. Correct?
Yeah. Yeah.
Yep.
So there will be that constraint we need to consider. Yes.
Yeah.
What is it then? Okay, if I am doing a bottom side view, what would my answer?
Yes.
Answer would be.
It depends like if you're doing the left first or right first.
2, 5, and 3. Yeah. No 7.
No 7 cause like 5 and 7 are on the same vertical line. 1, 5, and 7 are on the same vertical line.
Yeah.
So you can like just have either of
5 or 7.
and 7.
So in this case, what we have seen for the last time would be my answer.
At that particular level, quite possible.
So that means I don't need this condition. That's it.
So maybe you could use a stack in that case, or like as your value in your map.
No, why I need a stack? I just need that. I don't need that condition. So whatever C for the last time would be my answer.
Right. So to get like the last element that you see, you could just pop the stack at each.
It will overwrite anyway, right, in the map.
Yeah.
Okay. Yeah.
The trick is to get an agreement with your interviewer how the line looks like. So 5 and 7 are on the same line, and so first thing, the agreement is how the line thing should be defined. In this case, 1, 5, and 7 are on the same line, and basically, and 5 and 7 are again kind of can overwrite each other because they belong to the same what longitude or latitude what we have. Thinking like Earth kind of thing.
Yep.
Cool then.
Yep, that was interesting. Yeah.
It's good. Like we can stop the recording and then maybe people can stay for another 5 minutes if they want to.
I'll put this in the chat.
Okay. Thank you everyone for joining. I'm stopping the recording.
Thank you.
Okay,
Yeah,
thank you.
thank you, Hanif. Thank you, Azim.
Thank you.